everyone.
Hello.
Good morning or good evening or good afternoon. My name is José Luis Güntzel, and I have the honor and the pleasure of introducing you Daniel Menard and Wassim Hamidouche, who kindly have accepted our invitation to give the talk toward real-time implementations of VVC codecs. So I'll begin by giving a small, the short bio of our invited. Daniel Menard received the PhD and the habilitation degrees in signal processing and telecommunications from the University of Rennes in 2002 and 2011, respectively. Since 2012, he is a full professor at INSA Rennes, Department of Electrical and Computer Engineering, and he's a member of the IETR lab. He has 20 years of expertise in the design and implementation of image and signal processing systems. His research interests include low-power video codecs, approximate computing, and energy consumption. Wassim Hamidouche received the master's and PhD degrees, both in image processing, from the University of Poitiers, France, in 2007 and 2010, respectively. From 2011 to 2013, he was a junior scientist in the video coding team of Canon Research Center in Rennes, France. He was a postdoctoral researcher from 2013 to 2015 with Vader team of IETR, where he worked under a collaborative project on HEVC video standardization. Since 2015, he is an associate professor at INSA Rennes and a member of the Vader team of IETR lab. He has joined the Advanced Media Content Lab of IRT Research Institute as an academic member in 2017. His research interests include video coding and multimedia security, and he is involved in the MPEG standardization process. So thank you again for having accepted our invitation. And please, Daniel and Wassim, the floor is yours.
Okay, thank you. Thank you very much, José Luis, for the kind presentations. So I will start this presentation toward real-time implementation of VVC codecs. That I will present jointly with my colleague Daniel Menard. To start first, I would like to give the context. So the context of the presentation is the increase in video traffic. And the video traffic is especially, this increase is especially caused by many reasons. And we find here that this increase is caused by the new video streaming applications like and gaming platforms like Netflix, YouTube, and Twitch. And also the emerging new video formats like 4K resolution, 8K resolution, and 360-degree formats. And recently we have this COVID situation with the remote working and everyone having this remote video. And this is also increased a lot the video traffic. And in total today, we have around 82% of the video of the global and of the video of the global internet traffic represented by video. And this is also responsible to 1% of the greenhouse gases emissions. So this new situation brings many challenges to the video coding community. So the first challenge here is to provide high quality of service, even in this condition of increasing video traffic. And we can, as we can see here today, we have many video coding standards, like we can have AVC, HEVC, AV1, EVC and VVC, I will explain later. And we have to, the second challenge is to ensure the interoperability between all these video coding standards. And the third challenge is to reduce the energy footprint of the video coding. which represent of the video traffic, which represent 1% of the global greenhouse gases emissions, and which is equivalent to the emissions of a country like Spain or the global CO2 emissions of cars in 2025. And the last challenge is to also ensure a high quality of service for not conventional image and videos, which enable immersive visual experience and more realistic experience, like 8K, 360, point cloud, and light fields, that also enable up to 6 degrees of freedom visualization. So this presentation will be split in 3 parts. So after description of the context and the challenges, I will first present like a brief description of the VVC standard and its performance. Then my colleague Daniel will present complexity reduction of VVC encoding, and I will back also for the third section to present our decoder, Open VVC, which is efficient software VVC decoder. So I will first start by describing the standardization process for the VVC. So VVC has been standardized by ITU-T and ISO-IEC jointly by their 2 groups, VCEG and MPEG. And this is the effort of between 2013, after the standardization of HEVC, to 2020. So VVC have been standardized in July 2020, and compared to AVC, which has been standardized in 2003, then HEVC in 2013, VVC brings higher coding efficiency and enables also high resolution video coding like 8K, 360 degree, and HDR. And as we can see here, we have 3 main advantages of VVC compared to HEVC. So it brings a higher coding gains compared to HEVC, and it also defined in one main profile several tools like screen coding tools, and also we can find in this main profile resolution adaptation and also scalability, which was different from HEVC and AVC, that this enhancements have been proposed later, not in the main profile, but under extensions. So now if we go to have a look to the coding scheme of VVC, it is the same it is following the same coding principle than HEVC and AVC. It follows the hybrid, what we call hybrid prediction and transform coding tools. So as we can see here, first the video is split into blocks, then using a multi-type tree, and this the size of the blocks will follow the local activity of the pixels in the image. Then each block is predicted with using intra or inter predictions, depending on the image type. And then the residual between the predicted block and the original one, it is encoded with transform to decorrelate the signal, and then quantization to remove not important information. Then the encoder also have this perform decoding to decode the frames that are used as a reference to encode the next frames. So it performs inverse quantization, inverse transform, and then once the frame is reconstructed, it's processed 3 in-loop filters to remove coding artifacts and also enhance the visual quality of the image. In VVC, we can find mainly 3 in-loop filters, which are deblocking filter and SAO filter, sample adaptive offset filter, which was already present in HEVC, and they added the ILF, which is the advanced loop filter, which brings a high coding efficiency and also some complexity and increase, as we can see it later. And then once we have this reference frame, it is provided, it can be used for prediction, for intra prediction or inter prediction. But we can see here also in VVC, we can perform what we call combined intra and inter predictions. So to summarize these slides, here we have the coding, the blocks or tools of VVC encoders. It follows the same coding architecture than the previous standards, but it's bring improvements, individual improvements at these different individual blocks, for example, transform, quantization, partitioning, in-loop filter, and intra and inter prediction. Today, I will not have time to present all these improvements, but I will focus on two main tools, which are the block partitioning and also the transform. So for the block partitioning, VVC uses what we call multi-type tree partitioning. So it starts from a block of size up to 128 by 128 pixels, and then it can be split into 6 different configurations. As we can see here, in HEVC, we have just 2 possible splits, so no split or split into quad tree. In VVC, we can split a block into 4 other modes, which are what we call here binary splits or ternary splits. And this binary and ternary splits can be split into horizontal or vertical directions. As we can see here on the right, if we apply this 6 splits, we can have this partitioning of the CTU, and each small block here, it represents what we call a coding unit or a CU. And we can see with this more partitioning modes, we can have more flexible partitionings that follow accurately the local activity of the pixel, enhancing the coding efficiency. So what we can see also for the partitioning, what is new in VVC, that, for example, for the intra blocks, we can have 2 different partitioning for Luma and Chroma components. And for inter blocks, we have only like the Luma and Chroma blocks share the same partitioning as it was in HEVC previously. So now if we move to the transform block, VVC use 2 type of transform, what we call them primary transform and secondary transform. So the primary transform, it's like separable transform we use also in HEVC, but in VVC, we use what we call multiple transform selection. And so the encoder will select which is the best transform and then signal it in the bit stream. And especially 3 different transforms have been designed. So DCT2, which is also used in HEVC, but here we can go up to 64 by 64 blocks. And also we use DST7 up to 32 by 32 blocks. And we use also DCT8 up to also 32 by 32 blocks. And the encoder will select for each direction, horizontal and vertical, the best configuration that minimizes the rate distortion optimization, the rate distortion cost. So when we perform like the multiple transform selection, this primary transform, so when DCT2 is used, we can perform also this no-separable transform. And the no-separable transform is perform low-frequency, non-separable transform that's enabled to decorrelate more the coefficient that has been already processed by DCT2. And here the decoder performs the inverse LFNST first and then inverse MTS to recover the residuals at the decoder side. As we can see here in the right figure of these slides, at the decoder side, we perform the inverse LFNST, and for LFNST, we can have up to 8 different kernels. And then when we have this inverse LFNST, we can perform inverse DCT2 for horizontal and vertical direction, since it is separable transform. Or we can have also 4 other combinations between DST7 and DCT8. And we can also skip the transform LFNST and the transform skip. And it should be noted that LFNST is used only when DCT2 is used as primary transform. So now I introduced very quickly 2 tools, the partitioning scheme and then the transform block. Now we will see what are the performance of VVC compared to HEVC. In this figure, we show the bitrate gain, which is like the bitrate reduction provided by VVC compared to HEVC in terms of PSNR for the same PSNR quality. And here we have to provide the different VTM. So the VTM is the reference software of VVC, which is compared to the HM, which is the reference software of HEVC. And we can see that during the standardization process between VTM 2 to VTM 10 and then VTM 12, we have some significant gain compared to HEVC. For the blue curves is for all Intra configuration. We can have up to 25% of bitrate reduction. And for random access configuration, we can have up to 38% of bitrate gain on the VTM 12 version. This is corresponding from VTM 10, it's corresponding to the standard since the bitstream is fixed. Is only some slight modification have been integrated after in the new versions and bug fixes. So what we can see here to conclude, VVC brings significant quality enhancement, around 25% for all Intra configuration and around 38% in terms for random access configuration. This is based on PSNR, which is objective quality metrics, which is not perfect. We have also performed some subjective evaluation, like under standard condition of viewing with many subjects. And here I give an example of this sequence, kata and robot, which is in two resolution here, HD and UHD 4K. And we give here the MOS, the mean opinion score versus the bitrate. What we can notice in VVC in dot lines performs a higher MOS quality than HEVC in this continuous line. And what we can provide here, for example, in the excellent quality area between 80 and 100 quality score, MOS quality score, we can have up to 50% of bitrate reduction for HD resolution. And we find also this 50 bitrate reduction for this under this excellent quality area for the 4K resolution of the cat and the robot's video sequence. So of course, with this evaluation study, we performed the evaluation of over 7 video sequences encoded in HD and 4K resolution. As we can see them here under the temporal and spatial informations. We can see here that in terms of MOS, VVC brings 37% bitrate reduction for HD resolution and up to 40% of bitrate reduction for 4K resolution, which is slightly higher than other metrics, quality metrics, which are objective, like PSNR, SSEM, and VMAF. And we can see here that SSEM is the closest to the MOS scores, the mean opinion scores. Then I will talk about complexity of VVC reference software compared to HEVC reference software. Here we give the encoding time complexity versus the different VTM version. As we can see here, for all Intra configuration in blue, the complexity of the VTM has increased by 25 times the complexity of HEVC in all Intra configuration. In random access configuration, as we can see here in the orange color, it has increased but by 8 times compared to HEVC. So what we can see here that the bitrate reduction provided by VVC comes at the expense of higher quality at the encoder side, which is around 8 times the HEVC complexity. Now, what about the decoder complexity? Decoder complexity compared to HEVC decoder HM implementation, it is more moderate, and it is around 2 times the complexity of HEVC decoder, which is acceptable and affordable for real-time implementation on different devices. As we can see here, the complexity of the decoder vary a little bit during the standardization process. And finally, we can find that it is around 1.8 to 2 times the complexity of HEVC decoder. So here we see the repartition of the coding tools in random access coding configuration. On the left, we have HEVC at QP32 for UHD video, and on the right we have the VTM, so the VVC repartition tools. So what we can see, what is common for HEVC and VVC, like under the VTM reference software and HM reference software, we have the motion compensation, which takes the highest complexity around 46 for HEVC and 43% under the VVC. And what is also new in the VVC, that this adaptive loop filter, which doesn't exist in HEVC, that takes also around 37% or 37% of the decoding complexity, which is the second complex tools of VVC decoder compared to HEVC that use also only SAO and deblocking filter, which are less complex than the INF. So now if you want to compare, like in these slides, we compare like 4 different codecs. So we compare like HEVC and VVC. And also the EVC is the essential video coding developed also by MPEG, and we compare them to the AV1 developed under the AOM consortium. So all this comparison has been performed under the VVC common test condition in random access configuration, and we have 1 on-char frame by second. And here in this table, we show also the bitrate performance, all are versus the HEVC HM encoder. What we can see in terms of PSNR, MS-SCM, and VMAF, that VTM brings the highest bitrate reduction in terms of PSNR, MS-SCM, and VMAF compared to AV1 and EVC. And then EVC comes the second, and then we have AV1 in the third position. Now, if we compare this codec in terms of complexity, like here encoding complexity and decoding complexity compared to the HM representation, as we can see here, the VTM encoder is have the highest complexity, which is like 13 times the HEVC encoder complexity, AV1 5 times, and EVC is around 7 times. At the decoder side, as we saw before, we have 2 times more complex. VVC is 2 times more complex than HEVC. AV1 is less complex, decoder is less complex than HEVC, and EVC is 1.5 times more complex than HEVC. So if we draw these numbers in terms of 2D curves, as we can see here is the bitrate gain in terms of VMAF versus the encoder complexity. We can see like the VTM or VVC brings the highest coding efficiency, but it is the highest encoder complexity. Then we find the essential video coding at the second position with lower complexity, and then AV1 at the third position, but with low complexity, only 5 times more complex at the encoding time. At the decoding times, we find the same coding efficiency. VVC is the highest, is the more efficient in terms of coding efficiency, but double the complexity compared to the HM. For EVC is less complex decoding, and for AV1 has even less complex than the reference HM we can see here in this bound and in this bound for encoder and decoder parts. So this is the end for my part. I give the floor to my colleague.
Okay, thank you, Wassim. So now we'll go on the part about complexity reduction for VVC encoding process. So as mentioned by Wassim, the decrease of the bit rate comes at the expense of high increase of the complexity. So you have a factor 25 for All Intra profile and a factor 8 for random access. So why we have this high increase? So this is due to the rate distortion optimization process. So rate distortion, the goal of this process is to minimize the rate distortion cost, which is expressed with the following formula, including the distortion D and the rate R, and you have the Lagrangian multiplier lambda used to favor more or less one of the two elements. So this optimization process can be seen as a combinatorial optimization, where you have multiple decisions. So the goal is to you have different level of decision, and you have to find the optimal mode parameters, which are here alpha, beta, gamma, and delta. And these parameters belongs to a set of mode candidates. And the complexity of your encoder will depend on the size of each set. So to illustrate that with the case of VVC, so the first level is the tree partitioning. So as explained by Wassim, compared to HEVC, where you have two alternatives, split or a QT quad tree split. In VVC, you have 4 other alternatives. You can have binary tree, vertical and horizontal, and ternary tree, vertical and horizontal. So you can have up to 6 alternatives during your encoding process. So then you have to decide if you perform an intra-prediction or inter-prediction. So for inter-prediction, you will predict your block of pixels from your neighbor, the neighboring pixels. And in case of inter-prediction, you predict your block of pixels from a block belonging to previous or following frames. So if we go in the detail of intra-prediction, like in HEVC, you have regular modes. So you have 2 specific modes, which are DC for flat zone and planar for surface fitting. And then you have 65 angular modes. The number of angular modes has been multiplied by 2 compared to HEVC. So these predictions are made from the pixel in the column on the left of your current CU and on the row above your current CU. So this is the line 0, but in VVC you can take other reference. So this is the tool named multiple reference line, where you can use line 1 or line 0. Line 1 or line 3, excuse me. In this case, you have some restriction. You can only use the 6 most probable mod, which limits the number of mods that you have to encode. Another tool introduced in VVC is intra-subpartition. So you can split your CU in 2 or 4 partitions, and it can be horizontal and vertical. And the specificity of this mode is that each partition has the same intramode. And the last tool is the weighted intra-prediction. The idea is to make the precision from matrix multiplication. So you take the pixel on the column on the left of your CU and the pixel on the row above your CU. It leads to a vector. You subsample by averaging. This vector is multiplied by a matrix, and then you interpolate. So it gives you at the output a matrix, and you interpolate in order to recover all the samples at the output, and it gives you the prediction. And in this case, you can choose one matrix among up to 32. So this is for the intra-prediction, and then you have the transform. So as explained before, you have a separable transform. So for horizontal transform, you have four choice. It can be DCT2, DCT8, or DST7, or you can skip the transform. And after, for DCT8 and DST7, you can, for the vertical transform, you can use two alternatives. So as you've seen, you have a big tree of solution to test, and this is why you have a huge search space to explore. So the goal will be to try to minimize this, to reduce this search space. So it is interesting to evaluate the opportunity that you can obtain with complexity reduction. So the idea is to determine the limit that we can obtain if we are able to find, to predict the optimal solution. So for that, what we can do is to have a two-pass encoding. First encoding with exhaustive search. It gives you the optimal encoding parameters. And then you have a second encoding where you only perform the encoding for the optimal solution. You evaluate the encoding time for both cases, and for that, with that you can compute here what we call the complexity reduction ratio, which is computed for the case of 4QP. And you can evaluate for the different level what is the complexity reduction ratio that you can obtain. So if you consider that you are able to find the optimal solution for the partitioning level, you are able to reduce the complexity up to 97%, which is very high. In the case of intra-prediction, so the experiment has been conducted only for intra profile. In the case of intra-prediction, the reduction is around 65%, and it is 55% for the case of multiple transform selection. And after, if you are able to find the optimal solution for these three levels, you can go to a complexity reduction to up to 99%. So, and now we will go more in the detail of the complexity reduction techniques. So you have two strategies. The first one is to limit the source space by testing less configuration. So this is what I will explain in the rest of the presentation. And the other alternative, which is less used, is to reduce the complexity of each test. Instead of performing the encoding process to evaluate the RD cost, you estimate the RD cost with prediction techniques. So the first, the straightforward approach to reduce the complexity, it's to do it, it's to apply this search space reduction at the design of your encoder. You modify your encoder configuration in order to limit the search space. So you can apply it at two levels. It can be for the partitioning tree, where you can restrict the depth of the tree that you explore, or it can be by selecting the tools that you will use. So indeed, to obtain efficient bitrate reduction, numerous coding tool has been added in VVC, integrated in VVC. And each tool provides its gain in terms of bitrate reduction, but also add a complexity. So here you have the result of an interesting study conducted by Interdigital. They have analyzed the gain provided by each tool and the complexity. So on the x-axis, you have the complexity, the execution time, the encoding time, and on the y-axis you have the quality degradation that you obtain if you remove one tool. So, for example, if you remove the ternary tree, which is the point here, you divide by 2 your complexity, but you degrade your quality of 2.5%. So with this kind of analysis, you can select which are the best tools to integrate, to consider in your encoder. And the second strategy is to limit the depth of the tree, especially the binary and ternary tree. So this is what has been used in the VV-ENC encoder. So this is an encoder developed by Fraunhofer, and it is derived from the reference software DTM. And they have integrated a lot of optimization based on parallelism. So here you have the result obtained by exploring different depth for the binary and ternary tree, and you can select different depth for intra and interprediction. So they have explored depth between 0 and 4, and they are associated with different presets for your encoding. So if you look at the result between this point, which is the case of a bit depth of a tree depth of 4, and this point here with a tree depth of 0, it means that you do not use BT and TT. So this is the case of HEVC. You have 1 order of magnitude in terms of encoding time. So you see that you can have significant improve by reducing this tree depth. So now we will, the technique presented before, they do not take into account the content of your video. So now we will go, we'll detail technique analyzing the content of your video. And according to the content, they reduce the search space by selecting a set of solutions to test. So this is the first strategy. You predict the most interesting configuration to test, or you can use early termination. So the idea is when you evaluate a solution, you stop this exploration of the solution if you consider that it cannot lead to the optimal solution. So you have different kind of techniques to reduce the complexity. I will focus on 2 techniques, and I will speak more about tree partitioning because this is the most interesting level to optimize. So you have technique based on previous encoding decision. So for example, you can analyze the RD cost of the block around your CU or in the previous frame, and decide of the solutions that you want to test. Other techniques are based on the content of your coding unit. So you can have a spatial texture, analyze spatial texture or motion information in the case of interprediction. And the last kind of technique is based on machine learning. So you can use classification with uncrafted features or more advanced technique with convolutional neural networks. So the first technique that I will present is based on classification with uncrafted features, and we use spatial texture and motion information. So for these techniques, in terms of feature, we have 2 kinds of features. So it's based only on the current CU data. We do not use information coming from the neighbors in order to be able to parallelize this process. So we focus on the luminance sample values and the motion divergence fields. So it corresponds to the motion vector of the 4x4 subblock of your coding units. And we have evaluated 31 features, and we use the mutual information in the classification process in order to select the best features to use. So the technique is based on a binary classification, and we use the decision tree with a random forest. So the first decision is to decide if we split or not the current CU. If we split the CU, we will decide then if we use a quad tree or a binary tree. And in case of binary tree, we have to decide if it is horizontal or vertical. So this technique has been developed at the beginning of the standardization process. So at this moment, the ternary tree was not integrated in the VVC. So we have adapted this method for the new version of the multi-type tree, and we consider that TT and BT horizontal are grouped together, and same things for BT vertical and TT vertical. So the random forest give you at the output of the tree a score. So if you're with this score, you take a decision if your classification is, for example, class A or class B. So if you are close to 0, you can decide that this is class B. If you are close to 1, it is class A. But if you are in the middle, you take a risk by deciding if it's class A or B. So what we have done we have defined a risk interval, and in this risk interval, we do not take a decision. We consider the two cases. So this risk interval, the size of this interval can be adapted, and it will give you a trade-off between complexity reduction and quality degradation. So the results are provided here. We have in this graph, on the x-axis, you have the quality degradation with the Bjorn Dahlen bitrate. So the best is to be close to 0. And on the y-axis, you have the complexity reduction. So the red points are the points obtained when you reduce the depth of the multi-type tree. So you see that you can have a depth of 3, 2, or 1. And our solutions are given with the stars in blue, yellow, or green. So you see that for each MTT depth, we have a different point obtained by using different interval size for the risk interval. And just for results, you see that you can reduce of more than 60% your complexity for degradation of around 2%. So this technique has been proposed for intra and interprediction because we take into account of motion vectors. So now I will present a technique based on convolutional neural networks, and it is dedicated to only interprediction. So the idea is to use a convolutional neural network to extract the features. So the input of this CNN is a block of 68 by 68 pixels. It integrates a coding unit of 64 by 64, and we use 4 adjacent pixels on the left and above in order to take into account the pixel used for the intra-prediction. The output of the CNN is a vector of probabilities. Each element of this vector corresponds to the probability of a split at the boundary of a 4 by 4 pixel block. So the CNN that we have used is inspired by the ResNet network. It is made up of 11 layers, so it's a low complexity CNN with around 2,000 200,000 parameters. And we have done first tests to implement this kind of CNN on GPU, and we are close to real-time processing for HD frame. So this is the complexity of CNN of this CNN is low. So the second stage of this technique aims at deciding which kind of split that we will test according to the map of probability that we have obtained at the output of the CNN. So for that, we use a tree-based learning algorithm based on light GBM. And this is, excuse me. We use a multi-class classifier for each CU size. So we need 15 classifier, and this classifier can have between 2 to 6 output classes. So here you see the table which give, according to the size of the CU, which kind of split we consider. And the accuracy of this technique is presented here. So we have the classification accuracy. On the x-axis, you have the size of your CU of each classifier, the number of classes associated to the classifier, and you have on the y-axis the classification accuracy. For each case, we have up to 3 value. In yellow, it corresponds to the case where you select only the best solution. So this is what we call top 1 accuracy. In orange, it corresponds to the case of the 2 best solution, the top 2, and in red, this is top 3, the case where you select the 3 best solution. So by choosing the number of solutions that you select, you can explore the trade-off between complexity reduction and quality degradation. So the final result that we obtain with these techniques is presented here. So like before, on the x-axis, you have the quality degradation with the BDBR, and the complexity reduction on the y-axis. So we have tested different configuration. Each configuration defines the number of solutions that you test for each classifier. So you can see that you can have a solution leading to very low degradation, around 0.5%, but with a limited complexity reduction of 35%. And you can go to point leading to 2.5 quality degradation, BDBR, but you reduce the complexity of around 70%. Okay, so we will continue with now the decoder.
Okay, so I will continue with the presentation on our decoder developed in our lab, IETR. So it is called OpenVVC decoder. So OpenVVC is an open source VVC decoder, which is developed from scratch in C code. So the idea here is to provide consumers real-time decoding capability on different architecture, especially on x86 Intel, and also embedded platforms architectures like ARM. And also the decoder is considered as a cross-platform library that can run on different OS, especially like we consider the Mac OS, Android, Linux, and Windows. And here I provide the GitHub, it is open source, and then LGPL 2.1 license. Here I provide the GitHub, you can use it with any players I will explain later. So In terms of tools, the decoder OpenVVC supports all the tools that are defined in the maintain profile of VVC. For example, we can decode any bitstream encoded with the 4 different coding configuration defined in the standardization, like All Intra, random access, low delay P, and low delay B. It also supports parallel decoding on multi-core platforms with tiles. So the tiles that are a rectangular area of the picture which are decoded in parallel. This is a tool that should be activated at the encoder site. We can also perform frame level parallelism, and the idea here is to decode several frames in parallel, taking into account the temporal correlation between the frames. The decoder is also optimized in SCMD optimization for Intra and Inter tools, especially for the 2 platforms, Intel and ARM platforms. As we can see later, also it is very low memory consumption because it is also dedicated for embedded platforms with low energy, memory, and computing resources. And our decoder have been integrated successfully on different professional players. As we can cite here 4 players. VAccess Orca player is the player developed by VAccess Orca and Orange. FFplay is open source player. VLC, it is well-known player, used around the world, and GPAC player also developed by Paritech. So the OpenVVC decoder have been used in different demonstrator, and this is demonstrator with our industrial partners that it is the first demonstration in the world that have been dedicated to stream in live VVC VVC video on satellite. So here we encode VVC stream with using Titan Atom encoders in real time. Then it is packaged into TS format and then streamed on the satellite with the SES. And then the DVB receiver will receive the TS signal and then disencapsulated and then decoded with our decoder OpenVVC and displayed with the VLC player. This is like the first demonstration in the world using end-to-end VVC stream from encoding, packaging, and decoding and display. And here we target 4K real-time decoding on a laptop at 2 different rates. So as we can see here, 10 megabits per second and also 20 megabits per second to reach higher quality. And as we can see here, we can perform a real-time decoding up to 95 frames per second. That is enough to perform a real-time encoding of this video, which were encoded at 60 frames per second. This is just a snapshot of our demonstration with using VLC player that integrate OpenVVC decoder and enable to decode VVC streams on different platforms with optimization and parallelism that can be activated by default depending on the configuration of the platform. So here I just give some performance of the OpenVVC decoder. Here we have the number of threads used for the decoding on multi-core platform, which is here x86 Intel platform, including 8 cores. In all Intra coding configuration, here we have the frame rates. So as we can see here, without optimization, we have the lowest performance. When we added the optimization, we almost doubled the frame rate. This is allowed by SCMD optimization. And then when we activate the frame-based parallelism, we have almost linear speed up with using OpenVVC decoder here for the dot lines for HD resolution, and here the solid line is for 4K resolution. As we can see here, with 8 cores, we can have up to 100 frames per second decoding for all Ultra configuration. And compared to the VVDEC decoder developed by Fraunhofer, we have better performance in terms of a speed up, which is almost doubled thanks to more efficient parallel processing of the frames. Now, if we talk about the memory conception, here we also derive the maximum memory that can take the decoder according to the number of cores. And here we compare our decoder in green to VVDEC for two resolution, HD and 4K. So the solid line is 4K and the dot line is for HD resolution. And here the orange lines is for the VTM, which is the reference implementation of VVC, but it is not parallel, does not perform parallel processing. As we can see, our memory consumption is very low for HD and 4K resolution. Of course, it's increased with the number of threads because we allocate more frames in instances in parallel. But it keeps lower than the VVDEC and the VTM software decoder, which make it our decoder more suitable for embedded platforms with low energy, memory, and computing resources. So to conclude this part about OpenVVC decoder, was we can see like about the OpenVVC decoder and on this our presentation today, what we have seen today, that we can perform, as Daniel presented, we can perform efficient complexity reduction of VVC encoding with using machine learning and deep learning techniques. Today we have many software VVC encoders and VVC decoders. For example, Fraunhofer developed the VVENC software encoder, which is faster than the VTM, and our lab developed OpenVVC software decoders, which is also real-time. And we can start having some hardware decoders developed by some companies in France and over the world also. But hardware encoders are still under development, and today we don't have on the market like hardware VVC encoders. And what it is good also is to have some so what we need today is we need more optimization for VVC codecs to perform real-time decoding for higher resolution and decoding also. And this is needs to include some complexity reduction techniques and also like SEMD optimization and very efficient parallelism of encoding and decoding process. What we can also see, like in VVC, what we can do is to disable some tools. So depending on the quality we want to reach, we can disable or enable tools, and depending on the quality and also the trade-off between quality and the complexity we want at the encoder or decoder sites. So, just I want to, as future works, to go beyond VVC. So today we have AI-based VVC enhancement. So we use artificial intelligence to enhance the coding efficiency of VVC, as we can see it today for complexity reduction or also for quality enhancement or to perform the scalability. And if we want to go even further, today we have many, what we call them, learning-based image and video coding solutions that rely on auto-encoders to perform very efficient encoding. Today we have, we can perform with this solution better than VVC for Intra coding, but we can also perform better than HEVC for video in random access coding configuration. And we are organizing, Orange and Atom are organizing a workshop on AI video codings on November 25th. And also, if you want more details about the coding tools in VVC, we have just published a paper which is available in preprint on video coding standards, which gives a review on coding tools to consumer deployments. You can find more details about the coding tools in VVC and also real-time implementation of encoder and decoders and application with a relation with different other standards like DVB and 3GPP. So thank you very much for your listening, and please feel free to ask your questions. We will be happy to answer.
Okay, thank you very much, Daniel and Wassim, for the great presentation. We have a couple of questions for you. Iago Storch asked, is the parallelism of your decoder explored only on CPU, or do you use other platforms such as GPUs, FPGAs, and FPGAs besides the CPU?
For now, we only explore like the parallelism of the CPU. So, the decoder, like depending on the number of cores that can detect on the CPU, he can allocate optimally the cores to the ties or the frames, depending on the bit stream. This is done automatically performant. And what I can say about this today, for example, we have a demo on Jetson platforms, which is NVDA platforms that provide processing on ARM architecture. So we are able today, with 8 cores, we are able today to do 4K real-time decoding of VVC video, but we don't yet leverage the GPU part. So as future work, we will also see how we can perform some tools, for example, in-loop filters on the GPU parts of the Jetson NVDA mobile platforms. But for now, we just explore parallelism of the CPU.
Okay, thank you. So we have another question. Now is a question from Luciano Agostini. He said, I'm glad to have you both at our event. The talk was very interesting. And then he asked that if you could comment a little bit on the issue concerning energy consumption. Did you consider this issue, energy consumption, in some of your analysis?
So maybe so few words about the encoder. In fact, in the encoder, when you want to reduce the energy consumption, you have to reduce the complexity of your process. And maybe to use parallelism. So if you reduce the complexity, you will reduce the energy consumption. At the decoder side, it is more complex because you can have a high variation of the complexity of the decoding process during time. So it's not easy to find, for example, in your processor, the good frequency to do the decoding. Because you can have a frame with high complexity and frame with a low complexity. So if you use classical governors in your platform, you will overestimate the frequency and you will waste energy. So it's important to have advanced technique in order to try to estimate the complexity of the frame. And there is a group in MPEG working on grid metadata with the idea to provide inside the bitstream information in order to be able at the decoder to anticipate the complexity of the decoding process and to adjust to adjust better the frequency. Mm-hmm. So yes, for the decoder, the first goal was to have an efficient decoder in terms of execution time, and the next step will be to optimize the energy with a technique to select the best frequency with DVFS, for example.
Just completing a little bit this question. So actually, you didn't evaluate energy consumption in your experiments, right? You didn't measure.
In fact, for the decoder, we are able to measure the energy consumption. We have a tool evaluating the execution time and the energy consumption by analyzing some register inside your processor. But we don't have implement all the technique that can optimize efficiently the energy.
Okay, thank you. So now we have a question, actually, one question from Guilherme Correa. Thanks a lot for your great talk. Congratulations for the great contributions you presented. You presented a low complexity CNN for fast block splitting decision in VVC. Would it be feasible to run the CNNs in real time without GPU? I understand there is one CNN for each block size, so several CNN would need to run in parallel, right? I think
I will give more precision. In fact, at the difference of other technique, we don't have a CNN for testing each CU coding unit size. You have to do the inference of a CNN only for coding tree units. So in our case, this is a block of 64 by 64 pixels, and you do it only once. This is a multi-classification process which is done for each CU size. So our first idea is to use a GPU to do efficiently the computation, the inference of the CNN, and to do the encoding process on the CPU. If you want to use only a CPU to implement the GPU, to implement the CNN, excuse me, you have to do a lot of optimization. For example, you have maybe to prune different parameters inside your CNN to reduce the precision. And even with that, I'm not sure that you can have a real-time implementation.
Mm-hmm. Okay, thank you. Now we have a question from Daniel Palomino. Thanks for the great talk. Your decoder uses multiprocessing to achieve real time. This means that the encoding process needs to be performed in parallel, which breaks dependencies and impacts in the coding efficiency. Did you guys measure the coding efficiency loss of using parallel encoding?
Actually, it depends on the technique we use. For example, if we use frame-based parallelism, so we don't break any dependency at the encoder side. So we receive the bit stream and we decode it in parallel, but we have some restriction when we are in enter prediction. When we have enter prediction, we have to wait until the reference block is available to continue the decoding. So if we are in all Intra coding configuration, as I presented here, the parallelism is linear. So we don't lose, we don't have loss in terms of speed up because there is no dependency between the frames. However, when we have enter configuration, as we can see here, we don't have a linear speed up of the decoder because this this is enter dependency between the frames will have some weighting we don't have like a linear speed up compared to the number of cores. So we have a decrease in terms of speed up parallelism. But we can mitigate, we can have better performance even in enter coding configuration, but we have to use tile partitioning. But of course, if we activate tiling at the encoder side, we will have some loss in terms of coding efficiency. So it is always a kind of trade-off between speed up and coding efficiency. But at least even if we don't have any restriction of the encoder side, we can perform a perfect parallelism when we are in all Intra configuration. But when we are in random access configuration, we have lower speed up that we can improve with using tiles, but of course we have some loss in terms of coding efficiency.
Okay, thank you. Now a question from Claudio Diniz. Thanks for the excellent talk. Do you plan to develop also an open source VVC software encoder?
I don't think so. We are well recognized for developing a decoder. This is a huge work, and developing an encoder. It's a very long work, and people from, for example, in Finland, they have done it for with the Quasar in project in Tampere. They have done it for HEVC. I think that they will try to do it for VVC, but it requires, if you want to obtain something close to real time, it needs a lot of efforts, especially in the context of VVC. So yes, we do not plan to develop an encoder.
So actually our contribution at the encoder side will focus in providing some speed up techniques using AI that we can include in the VTM or also in the VV-ENC, which is the Fraunhofer encoders. But when we want to do real-time demonstration, we work very closely with our industrial partners like ATEM, VTech, and other partners to do end-to-end live demo with using their professional encoders.
Mm-hmm. Okay, so maybe you Wassim, has already answered the next question, which is from Andre. So he was asking if the presented techniques to speed up encoding, if they were implemented within the VVNC encoder, because I think he had took a look inside in the GitHub repository of your the encoder, and he didn't find any of those speed up techniques that you presented. So he was wondering where you put those speed up techniques.
So the results that we have presented today are based on the reference software VTM, and it's true that now our goal is to implement it in a more realistic encoder with VV-ENC, but this is not done yet.
Mm-hmm. Okay.
So, but this is our plan. It's to implement this technique in VV-ENC, mm-hmm, with the hope to be close to real-time encoding.
Okay. Okay. Thank you. I cannot see any other question, but I still have one question myself. So it's concerning slide 39. In slide 39, you showed your speed up techniques, and one of them was I think it was 39. 39.
39, yes, because I do not see the...
No, it's not 39. Oh, I think I didn't. It's the one that when you show the possibilities, I think it's the...
yes.
After this one, when there is the CNN and the other one. Sorry, I think I didn't.
Yes.
Well,
this one?
Yes.
Yes, this one. Yeah. So in the handcrafted features plus classification, what type of technique did you use to classify?
So here, what we have done, it was binary classification with a tree decision, like a random forest. But now the idea will be to test the case of multi-classification, multi-output classification. Yes, because this first technique has been done before introduction of TT. So you can, it was more or less the set of the sequence of decision was logic. Now it's more complex with, so I can show you here. Here it was logic to do first split or not split, and after QT and after BT. But now we have TT, and it's difficult to choose if we first test TT or BT. So that's why I think it will be more efficient to use multi-output classification.
Okay. Okay, thank you very much. And if you could send us more information concerning this event that you are organizing,
Yes. Mm-hmm.
and we could broadcast this to our groups, because I think it would be very interesting for us to, I don't know if it will it be open, or have to pay, or how will it?
No, the event with ATEM on Orange, it's free.
It's free. We have just to register, and we will provide you the link to register.
Great. Okay, so we would greatly acknowledge if you could send us more information on this event. Okay.
Yeah, there is a web page.
Mm-hmm. Yes.
There is a web page, and you can able to register it free.
I think it starts at 10 o'clock in the morning, so or 9 o'clock. So it would be early for you in Brazil, but if you are motivated, you can attend.
Sure. Okay. Thank you very much for.
Thank you for your invitation.
Yeah. Okay. Thank you. Bye bye.
Thanks. Bye.
Thank you very much. Have a good, nice workshop.
Okay. So we'll have a break now until 3 p.m. and then we'll have another session will be the Internet of Media Things presentation talk that will be given by Deborah Mushaloa Saad from the Fluminense Federal University. Okay, thank you very much, and we'll see you in 15 minutes, about 15 minutes, okay? Thank you, everybody. Yes?
There was a last question there, if we still have some time.
Like question.
From Marta in the chat.
In the chat, there is another question. I'm not seeing, can you see it? From
Marta Luz.
Oh yes, congrats for the great talk. Are you working on any intern prediction complexity reduction in VVC? Okay.
In intra prediction, yes, we have started to work on this. But as I have shown, the opportunity of prediction will be lower. But it is interesting to try to predict the intra mode in order to continue to reduce the complexity. But if you analyze what is done in the VTM, because you have a lot of choice to do in the intra prediction, and there is still techniques to reduce the complexity in the intra prediction in the VTM. For example, you have root mode decision which are do not encode completely the solution. They select some mode to test and not all the angular mode, for example. So there is still complexity reduction techniques. So the gains that you can obtain will not be so important as in the case of tree level.
Mm-hmm. Okay, thank you very much. Thank you, Guilherme, for calling my attention. And sorry, Marta, I almost forget you. Okay, so with this, we came to the end of our session. Thank you very much. Merci beaucoup, Daniel and Wassim. And I will see you in 15 minutes now, from now in 15 minutes, okay? Thank you, bye-bye.
Yes. Bye. Bye.
Bye, au revoir.
Bye, au revoir.
Au revoir.